Good evening, and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This is part one of the lesson on differentiating exponentials and logarithms, and in this lesson I'm just going to be talking about how to differentiate e and e when there is a function incorporated into it. So you should already know from previous work on exponential rates of change that if you have y equals e to the x, you get dy dx equals e to the x. E is known as the exponential function because it has the very special property where it differentiates to itself. If you were to draw a tangent at any point on the curve y equals e to the x, the value of the gradient would be the same as the value of the function, the y coordinate. If you extend that to be y equals e to the power of kx, where k is a number, then when you differentiate you get k e to the power of kx, so you multiply by k. And you would have needed to know that for exponential rates of change, but no more. So what we're going to do is just extend that to say, well, why is it that you multiply by k? The reason that you multiply by k is because it's another application of the chain rule. It's the derivative of the power. So what that means is, if I have e to the power of a function of x, then when I differentiate, the e to the power of f of x bit stays the same, but I also multiply by the differential of that function. So the e bit stays the same, times by the differentiated power. And if you think about, okay, well, what does kx differentiate to if k is a number? Well, it differentiates to k. So it makes perfect sense. So what I'm just going to do now is 4 quick examples of differentiating e to the power of a function and looking at how that works. The first one is y equals e to the power of 8x plus 1. So if I differentiate that, remember the e bit stays the same. So it's e to the power of 8x plus 1. But I multiply by the differentiated power. So I differentiate 8x plus 1, I just get 8. So I would write that as 8e to the power of 8x plus 1. Same logic here. Y equals 5e to the power of 7x squared plus 3. So my dy dx, the e bit stays the same, including the 5. So 5e to the power of 7x squared plus 3, multiplied by the differentiated power. 7x squared plus 3 would differentiate to 14x. And I've just tidy that up by multiplying 5 and 14x to get 70x e to the power of 7x squared plus 3 for dy dx. So e bit stays the same, multiply by the differentiated power. Should be getting the hang of this by now. I should have been having a go at it and pausing and restarting. But e to the power of 4x cubed, I'm going to have e to the power of 4x cubed stays the same, multiplied by the differentiated power, which is 12x squared. And how I would write that is 12x squared e to the power of 4x cubed. Finally, y equals e to the power of 3x squared minus 2x. So dy by dx, the e bit stays the same. E to the power of 3x squared minus 2x, multiply by the differentiated bracket, which would be 6x minus 2. And crucially, I put a bracket around that because it's 2 terms. And that affects how I then write my result, because I would be writing that dy by dx equals 6x minus 2 in a bracket, e to the power of 3x squared minus 2x. As an extension to this, when you come on to integration, you're going to have to look at functions that look like this and think about how to reverse engineer them to integrate, thinking about how you would have differentiated to get to that in the first place. That might be something you just want to have a little think about. You look at these 4 results on here. The key thing to take away from it when you're differentiating e's, the e bit stays the same and multiply by the differentiated power. That's job done. I'll see you in the next video.